I'd like to get started by talking a little bit about your test. And if you don't mind, I'll probably record this little spiel and do it as a separate small video and put it on the main page of Canvas. So if you have to go and say, what did he say again, you can just watch that piece of the video. And just as I start talking, some people come up. So you are going to be doing your test on Monday. And your test is going to be from 1 till 3, so that's 2 hours. And it's going to consist of 20 questions. And it's going to involve all the stuff that we've done in the first half of the quarter, right? Week 1 to 8 today. We'll finish off chapter 6 today. And once that's done, then you have got chapter 6 to get finished this Sunday. So your homework is now, this particular one is now due on Sunday coming. Now what you should be looking at here, I hope, is our Canvas page. So you all should know how to get to your class's Canvas page, right? And you are going to, where is the done thing? I'll click on this. And maybe put it over here. And I'm going to switch. Uh-oh. Something bad happened.
I'm here.
Things are disappearing as we speak. This is not good. Okay. My computer is just being weird beyond weird.
Is this still working?
I don't know if it's still working. Are you seeing Adobe link on that screen?
Yeah.
Okay, so we are working. I'm going to try and turn the sound level down, otherwise I'm going to go deaf. It's not your fault that my speakers are screaming at me. Okay, I'm going to try that level, see if that works for us. Okay, so let's just wind back. In our case, here's our stats class. If you watch, if you go to the link, there's a piece of software you're going to download called Adobe Scan, and it clicks on there. And essentially, you use your phone, take pictures of your work, right? The written work that you did to get the answers. Now, not every question requires working, and I understand that, but anything that does, you should do the working for, because at least you'll get partial credit. So you'll download that. There's a version for Android phones. There's a second version if you get an Apple phone. If you don't have a cell phone, which is, it happens, get a scanner or borrow someone's phone, and you can do it that way. Now, what will happen is that on WebAssign, you'll go to WebAssign, and that's where your test, your midterm test is going to be, and it won't be visible until 1 p.m. and then it'll just appear. And you do it just like you do homework, right? You put your answers in the boxes, you read the question, you use the salt boxes. In fact, a lot of the questions will look very similar to homework questions. And as you're going through some of them, the ones that you needed to do working for, you would write down the working for them. And when you're finished, you use that to Adobe Scan that I talked about, take pictures of your working. And once you've done that, you will go to this place. You see it says midterm exam. When you click on that, you will then be able, you can't really do it right now. Well, actually you could. Let me show you what that would look like. If I go into student view. So this is me doing that. If you click on that, you see that little red button, submit assignment? You hit in that red button. It says choose file. You click on choose file. You find wherever it is you stored your thing. There's my post-tenure agenda thing. You click on that and you open. And that's it. you walk away, you're done. So you need kind of two things to do. Let's leave that now. The first thing is you need to download Adobe Soft so it's in your phone. You turn up on Monday, usual class time, and at 1 o'clock the test will start, and 2 hours later it will close you out. So that doesn't normally happen with homework, but it happens with tests. At 3 o'clock you'll just get booted out. So you really do only have 2 hours to do it. And then you've got about half an hour to take a picture of all your working. You shouldn't need that much time, but you've got half an hour to do it, and then you send it to me. Does that seem, you understand the process now? Now, I've got a couple of, yes, question?
Yeah, I have one question.
Mm-hmm.
So we're going to be doing it on WebAssign, right?
Right.
And then I guess for parts where we would need to like write out some stuff to kind of work it out, that's what we would be taking pictures of and uploading, right?
Correct.
Okay.
You got it. Exactly that. And try and write as much as you can. And the reason I want you to do that is that WebAssign is notoriously cruel. If the answer is 12, you get the points. And if somehow or other you added instead of subtracted and you got 10, it gives you 0. And if I see you working, I can tell he switched 2 digits around, or he forgot to add a number, or whatever it is you did wrong. You can get partial credit. And another thing to do with the test is to reduce cheating and to prove you're not cheating, and you have to have your video on so I can see that you're not getting the answers off a book or so on. Now, I do have here what you need to know to do the midterm. Do you see that? Now, you click on that link. It's basically a PDF, and it tells you what you can and can't use. So there are certain things you can have next to you, and so on. And it explains, I hope, everything that you need to do. So are we kind of clear about how the midterm is going to work? It's going to be on WebAssign. It's going to last.
I had a question about the Adobe thing.
Say again, Carlos?
I just have a question about the Adobe scan.
Yes.
I've had a class with you before where we use Cam Scanner. Can we still use that, or?
Sure. Yeah.
All right. Thank you.
Cam Scanner, I think, costs money. So if you've got it, that's great. Adobe Scan is free. That's why I picked it. But other people might have other things as well. Some people have a printer and they just scan it and they get the PDF that way. Not too many people do it that way, but if that works for you, you can do it. All I want to get is a PDF and you upload it, right? So whatever way that PDF gets created, I'm okay with that. So are we good? We all know what the test is, right? If 1 to 3 doesn't work for you, and I would expect it should because it's virtually our class time anyway, then if it doesn't work for you, you shoot me an email and we'll arrange a different alternate time or schedule, whatever you want to call it, for when you do it. Hopefully it won't be anybody, but if it is necessary, we can certainly do that. Let's leave student here. And get over here. And let's get started.
Professor,
Cool.
I have a question about the
Yes.
homework. On one of the homework questions, I think it was question 4, they mentioned Pearson's index. Did we go over that in class?
No, we didn't. What question mentions that?
I think it was question 4, part D.
What you may want to do for that is just go and look at the ebook and find out what they're talking about and just figure it out from there.
Okay, I can do that. Thank you.
Yeah, I wouldn't get too, yeah, I didn't even know they had that. I got a whole load of charts, so I guess I should be reading them. Probably I shouldn't. People are just bothered about the wind. Right, so So we have only two sections to go. One homework is called 6.4 and 6.5, and it deals with something called the sampling distribution. Well, let's give you a little rundown of what that is. We've heard the term sample in population before, so this is a kind of refresher. Right, the best kind of sample in the world is called a simple random sample. How does that work? Well, this is the main property of a simple random sample. And it says that if every member of the population has the same chance of being chosen, in the sample. So imagine you had a population of, like Glasgow, which is about 600,000 people. A simple random sample of, say, 100 people would be, you choose 100 people from all of the people in Glasgow, and every single person in Glasgow had the same chance of being chosen as any other person in Glasgow. Which kind of makes sense. If you want to be a random sample, you want it to be a pretty random affair. Now, let's suppose you collect a sample. And let's just say that this sample had 100 people in it. And we were interested in the average age of people who live in Glasgow. And I did the average age of these 100, and the answer I got was 30 years old. Can you remember that symbol X bar? Doesn't that, and you read it out loud as X bar, isn't that the sample mean? So basically you added up the age of 100 people, you divided by 100, and you got the average ages 30. Well, the population of Glasgow does have a mean. We pronounce, oh, does anybody remember how you say that funny Greek letter? Sounds like a cow.
No.
That's it. And that is the population mean. Let's say we actually found everybody in Glasgow and got their age and it was 31. Is it a surprise that the sample of 100 didn't give me the exact answer for the entire population of Glasgow? Wouldn't it be reasonable to expect a little bit of difference, right? That seem reasonable? What would happen then if instead of doing just one sample, I'll call this X1, but I found another 100 people from Glasgow and I got their average age and I found X bar for them? Do you think this second sample would give me exactly the same average as my first sample? Would that seem realistic?
No.
No. Could I do this one and I get 32 this time? How come? Well, maybe I just got a few older people and a few younger people, right? Whatever it was. But doesn't the population, isn't its mean a fixed number? Right, it's 31 today, and it's right, it's 31. These guys, this fella here, are called sample statistics. Or just statistics for short. And this fella here is an example of what we call a population parameter. Or just a parameter for short. And the whole goal of taking a sample is to try and get an estimate of what this number is. Now, I know 30 isn't this number. Would you agree? At least it's pretty close. It's better than just guessing. You know, walking around a city and saying, yeah, the people in this city, they probably get an average of 40 or 22 or whatever random number comes out of your head. At least this has got some structure to it. Now, there are a number of sample statistics and population parameters that we have to be aware of, but they're not many. So I think I'll do that right now. So this is going to be a sample statistic. And next to it, I'm going to do what the equivalent population parameter that you're trying to estimate it with. Population mean, sample mean, right? So it's the means. That funny little guy there. You remember the Greek, that's a Greek letter, what that letter is, how you say it out loud.
Sigma.
Yeah. What does sigma measure? Population what? That measures the population mean, right? What's the average age of everybody in the population? What does this measure?
Standard deviation.
Right? SD for short. So mean of the population, standard deviation. Now, over on this side, you've got X bar, of course, and you've got a guy called S, typically, although I've seen it called SX. I've also, it's got a few names, but I'm trying to admit, I think the textbook uses that one of the three choices. I could be wrong. But that's the standard deviation of my sample. And if you remember back a few weeks, didn't we put that into a calculator and they just told us what it was? Because isn't that horrendously difficult to calculate? Remember, you had to take the mean and then get the deviation and square it and square root and all sorts of cool stuff. There is a third one that we haven't met yet, and we won't meet it here until next week sometime, I believe. There's a guy called P and a guy called P hat. This guy's called P hat. That's how you say him out loud. This guy's just called P. And he is measuring the population proportion. I'll tell you what that is. Suppose you asked every single person in Glasgow, have you ever been to France? The answer that will come back, like 32% of them have been to France. That number is a population proportion, right? Anything that is, you ask someone a question and the answer is yes or no, and you typically register the yeses. So you could ask them, are you going to vote in the next election? Yes or no. And the answer might be 62% said yes. The population proportion then is the percentage who say yes to a question. P hat is the statistic that does the same thing. But you can't ask everybody. You only can ask in a sample, say 100 people. So you ask 100 people, have you been to France? And 40 of them said yes. So P hat would be 40% or 0.40, because they very often write it as a decimal. Are we cool with these three guys? It's a bit of kind of notation and whatever you want to call it. You cool? Okay. Let's return back to our story. Suppose I kept on taking samples of 100 over and over and over again until I got fed up or tired. And every time I got a sample, I'll register it on here. So the first one I got was, let's put a 30 here, 20 here, 20, 32, 33. And so I got a 30, and I got a 32, and I got maybe a 31, and I got 31.5. And I just kept on doing it hundreds and hundreds and maybe even thousands of times. This is what you end up getting. You basically would get a big histogram that would have this shape. You recognize this shape? Don't we have various names for, you know, imagine this is really rectangles, right? But don't we have a name for this shape? What's it called?
Normal distribution.
And that's what I'm going to use. But I could have said it was a mound shaped. I think we've at least seen this term once. Didn't one of the questions call it a bell shaped? Right. Can I also call it unimodal and symmetric if I was being kind of technical? You know, it's just different names for the same guy. But we're going to do normal distribution. Now, if it's a normal distribution, which it definitely will be, it has two things that we want to know about it. We want to know what the mean would be, and we want to know what the standard deviation would be. This shape is called the sampling distribution. So that's where that heading comes from. Sampling, right, you're taking samples, and the distribution of them, right, how they can spread out through time. Now, in this story, the average age in Glasgow was 31 years old. Would it surprise you that the average of the samples is also 31? Not that every sample is 31, because that's definitely not true. But if you took all of the samples and averaged them out, it would be 31. I mean, if you did enough samples, wouldn't you end up asking everybody anyway? So in a way, it's not a surprise. What might surprise you is what the standard deviation of this is. And you might think, oh, well, let me tell you what it is. Let's say that for this, that the standard deviation, no, we'll make it 10. Nice round number 10, was 10. Right? Now, you might think that the standard deviation should be 10. But that's the population. And that's for everybody. You could pick somebody and it would be 10, 20, 30, right away from the mean. But not this guy. The standard deviation of this sampling distribution is actually that guy, which in this case is 10 over the square root of 100, which comes out very nicely as 1. Now you might think, why is this smaller than that, right? Why should the distribution for all these samples be much closer to each other than if you did the population? So here's my argument for why it would be the case. Let's look at the population. Imagine you took every single person in Glasgow and you found their age. Now we know the middle age is 31, right? But isn't it quite likely that you're going to pick up a baby occasionally? And it's not that unusual. Would you agree that you might get somebody at 60? Certainly bigger as well, right? It's not that unlikely then, right? When the standard deviation, what was it 10 here? Yeah, it was 10. Then it would go something like this. I wish that was a number like 30, but too late now. 41, 51, let's change that to 61. 21, 11, and 1. Can you see the 10, 10, 10 trick, right? So if I went and said, how unlikely is it to get a 41-year-old? Well, the answer is, yeah, there are a lot of people who are 41 or bigger. It's a fair chunk, right? Yeah. This is what the sampling distribution would look like if I did one on top of the other. Now, do you see it's much denser and probably taller to account for that? Probably should have made it a bit taller. So here's my argument. It's not that unlikely that you could randomly pick one person from the population and there's 41. But how hard is it to get a mean of 41? Don't you need to pick quite a lot of 40-year-olds so that the overall average is 41? Do you see that's kind of rare? If I go extreme, to get a 61-year-old, wouldn't that happen maybe 10% of the time? Yeah, you'll get a 61 or older person. Do you know to get a mean of 61, don't you have to have most of the 100 people that you picked all have to be 60-something? Because won't the rest of them be 10s and 12s and 8s and 20-year-olds? Now, isn't that much harder then? I don't know if that's convinced you. I hope it has. If it's not convinced you, will you go with, trust me, I'm a mathematician, and just go with that? So, the sampling distribution is normal in shape. It has a mean, the same mean as the population, and it has a standard deviation, which is sigma divided by the square root of n, where sigma is the population standard deviation, and n is whatever the sample size is. So far, so good? Now, let's suppose that I decide that I want to do not samples of 100, which we've just done, and it has a mean of 31, and it will have a standard deviation of 1. But I do samples of 10,000. Well, the mean will still be 1 in 31. The standard deviation, which is sigma over root n, is going to be 10 over the square root of 10,000, and that equals 0.1. What that tells me is, see if you do a sample size of 10,000, can you imagine that the answers you're going to get are going to be really, really close to 31 for virtually all of the ones that you could pick? Can you imagine a 0.1? It wouldn't really get much between here and here. Can you see that those are the two upper and lower ranges that a typical sample would be? Which means if you do a sample of 10,000, whatever number comes out, wouldn't you be pretty sure that you're damn close to the right answer? And what that's telling us is something that I think makes sense. Shouldn't bigger samples give you a more accurate estimate for where the mean is than small samples? And if I ask 100,000 people, wouldn't I be pretty sure that I'm getting the answer right to a decimal place at least? On the other hand, if I ask 2 people, could you imagine that that could be everywhere and anywhere? Right? It wouldn't be a very good estimate. So that is the theory behind what is called the sampling distribution. It tells us that if we get a sample of a particular size, I know it's going to be normal in shape, and I can even tell you what standard deviation is likely for it. So far, so good? Any questions? Looks like we're on a roll. Okay. And I'm going to show you some early questions from that homework. Okay. While I'm doing this, do you want to say hi so you can get attendance? The thing I've got's got all the answers in it, and that just distracts the heck out of me. Okay, I'm good now. So, everybody who's here said hi? Okay, ready to switch over. Now, question 1 is basically asking is what a simple random sample is. And I believe 2 of these work. They're just phrased in different ways. So there's, I guess I could call them numbers, right? The top one's number 1, the bottom one is number 5. Give me one of those descriptions that fits what a random sample is, a simple random sample is. If it's a bit small for you, yeah, hopefully that helps. Give me a number, 1, 2, 3, 4, and 5. Give me one that works.
2.
That's pretty close to the sentence I used, isn't it? So that's correct. What's the second description? The dogs are joining in. A simple random sample is, insert sentence here.
Come on, let's go. Maggie,
Last chance.
Maggie, come on. Let's go, 5.
You got it before I clicked it. Yes, it is. The simplest method of selection is used to create a representative sample. You know, a simple random sample is a good representation of the population. I guess that would be another way of phrasing it. Now, what is a population parameter? Well, here goes. A population parameter is a numerical, it's a number, descriptive measure of a population. And here is a list of guys. There's 3 of them. That guy, and that guy. Remember my list? This question here is basically the other version. I'll let you read that yourself. Now, I just realized I forgot to tell you a name. I thought I'd covered all of them, but I haven't. Remember the standard deviation of the sampling distribution? Remember that guy? The standard deviation of the sampling distribution is a bit of a mouthful. So they call it the standard error. So if you see the word standard error, it's a standard deviation of the sampling distribution. Now, I haven't talked about this one, but since the question is here, I can now do it. An unbiased estimator is a number that you get from your sample that you think is going to be pretty close to what the population number is. Right? So an example of an unbiased sample. X bar is an unbiased sample of mu. Right? The sample mean will probably get you pretty close to it. P is an unbiased estimator of P hat. We talked about that. Okay. We are now going to return back to my notes so I can start working on the next piece of the puzzle. Because we haven't really done anything numerical yet. We should. So this is going to be my version of question 10. Suppose that X has a distribution of mean of 70. So we're talking about the population here. And its mean is 70. And its standard deviation is 12. And we take a sample of size 64. Right? So that's just given information. And we are looking for they write it in a kind of funny way, so I'll try and explain what it is. They write it with a mu and a little x bar. I don't really like that notation, so let me tell you what it means. It means, oh God, it's a bad use of the English language. It means the mean of the sample. Isn't it annoying when the English language is a word that is the same word that you want to use that's totally unconnected to it? That is basically right. And the standard deviation fella is written like this. And we know how to get this fella. He's the sigma over root n guy. So in this case, we know it's going to be 70, and we know this guy's going to be 64. No, it isn't. It's going to be 12 divided by the square root of 64, which I believe is 1.5. So what we found out here is essentially that for the sampling distribution, the mean is going to be 70, and I'll call it standard error. I like that name, is 1.5. So can you imagine? That's what they call the standard error, is weird notation. And that's a little bit easier because it does kind of look like a mean. And then they ask you for this. This is question B. Find the z-score for a mean, it's an x bar, of 71.5. Well, when you do a z-score, don't you basically do data, take away the mean, divided by the standard deviation, right? That's it in English. And in fact, I think I should keep to the English. This guy represents the data. The mean that they're talking about is 70. And the standard deviation they're talking about is this fella called the standard error. And after all that hard work, its z-score is 1. Now, we would like to know this thing. What's the probability that you get a mean score less than 71.5? Well, unfortunately, or fortunately, I guess, I'm going to have to show you that because we should be getting good at this guy. Salt does those things for us. So I'm going to hit salt here. And it's a normal distribution. The mean is 70. The standard deviation was 1.5. Now notice I'm talking about the standard error, right? Not the population standard deviation, but the standard error, right? Is 1.5. And we would like to know what's the chances that that is less than 71.5. And the answer is 0.84134. Right, while I'm at this one, suppose I wanted to know the probability that it was bigger than 74. Right, did that answer? Suppose I wanted to know what's the chances that I get a mean and it's between 69 and 73. And not that number. There we go. And the answer there would be 72.72 and so on. So as long as I know these two guys, can I answer all the questions like what's the chance that I get one sample and it's bigger than this number, less than that number, or between two numbers? Does that make sense? Okay, so let's return to my result here. So this is just a technical problem. You know that they sometimes ask you for the answer to 2, 3, or 4 decimal places. Make sure that that's what you write down. So if they say I want the answer to 3 decimal places, it's that guy. If they want it to 2 decimal places, it's that guy. And if they wanted it to 4 decimal places, it's that guy. It's an easy thing to not pay attention to. So we are basically doing right now, this is an example of us doing one of these sampling distribution questions. I'm going to show you a use for it. I've used this idea before, so I'm going to use it this time. IQs are 100. The mean of IQs is 100. And the standard deviation is 10. That's basically the population numbers, right? And we think that football players' IQs are less than that. We think the average IQ of football players, because I pick on football players a lot, is less than that. So the question is, how do we go about finding evidence to see if that's true, or it might even be false, right? Well, you take a sample. So let's suppose that we take a sample of 400 high school football players. And we got a mean of 98. Okay, now how can that help us decide if that's unusual? Well, what we're going to do is we are going to find what the sampling distribution would be. And then we're going to look at what's the probability that somebody could get an IQ like this or even worse. And if that number is really small, then that means this is very unlikely to have just happened by randomness, like a bad sample. And the real reason why it's so low is because American football players do have a lower IQ than everyone else. So we are, I guess hoping is the wrong word, but we are looking to see what this percentage ends up being. And by that I mean, what's the percentage that you get a sample, right? Less than or equal to 98. So let's get the sampling distribution fella going. They want to call it this guy and this guy. So the only reason I'm using that funny notation is so that you get used to what numbers meant to go there, right? Won't this guy be 100? Okay. This guy is sigma over root n, 10 over the square root of 400, and 10 divided by the square root of 400 is 0.5. Now I'm going to find the probability that my data is less than or equal to 98, and it's going to come from a normal distribution with a mean of 100 and a standard error of 0.5. So I'm now going to go back and I'm going to use salt to do that calculation for me. Well, the IQ is going to be a mean of 100. It's going to have a standard deviation of 0.5. What's your gut feeling telling you? Is this going to be small? Do you think the chances that you get a sample mean of less than 98 is going to be a very rare thing, a very small probability? Let's see if it is then. And the answer, oops. Make sure I click the right guy. Uh-oh. 0.00003. That is the evidence that we were looking for. So here's the argument for why that's evidence that football players have a lower IQ than the general population. If they had the same kind of IQ spread as everybody else, wouldn't that average be pretty close to 100? Which you might say it is. But according to what we've calculated here, the chances that you got this number or anything less is extremely unlikely if this was true. So if it can't be that they're the same, the alternate must be true. Isn't the alternate then that they must be less than 100? So
Yes.
it's a bit like you set something up to shoot it down. Right. We'll assume that it is 100. If it was 100, how likely is that? Ain't going to happen. It can't be 100 then. I had the question and I interrupted you. So what was it you were asking?
So is the X with the line over it that says 98, is that the average of the sample?
Correct.
So then how come you're not using that in the other equation? Because isn't the M with the X line over it subscript, isn't that supposed to be the mean of the sample, not the mean of the overall?
This number is the mean of the population. The
Okay.
mean of the sampling distribution is the same thing as the mean of the population.
All right, so whenever you see that M with the subscript X, it's the mean of the population.
Yes.
Okay, I have it marked down wrong, my bad.
Okay, now if you do this guy, he will be sigma, the population divided by root n. So do you see this number will not be 10. This number will always be whatever this one is. So the new x bar is this, and the sigma x bar is this divided by the square root of n. So we've got a way here of deciding, is a subgroup of people similar to the entire population? You can certainly enter quite, what's the word I'm looking for? You know, like eugenics and Hitler and fascists and things, who try to change these values by various laws of who can breed with who and so on and that kind of thing. Very nasty part of history. But that doesn't mean that it isn't true that generically different groups have different attributes in certain places. IQ actually isn't one of them. IQs are pretty standard throughout the world. There are some populations whose IQ is higher, but they're not specifically anywhere in particular. Right? Korea has got a higher than average IQ. Finland, totally different place in the world, has a higher IQ. Scotland, I think we just smidgened it like 0.1 above the average. Nothing to talk about, right? Nothing wrong with that, right? It's culturally different, whatever. But you don't want to kill people and do things just because of that. It would be a bad idea. Next fella then. Oops, get that guy out of the way. Which one shall I do? Oh, here's a quick one. I don't know if you can see this question, so let me double check that you're on it. We're back to the homework thread again. Bouncing up and down like a yo-yo here. Suppose that you have some data and it's distributed. So this is population we're talking about. 82 and 8. If you take a random sample of 16, what can you say about the distribution of X bar? Won't it mean the 82? But what is the standard error? I'd prefer to call this weird guy standard error. Well, shouldn't the standard error be sigma, which is 8, divided by the square root of this number? Okay? And 8 divided by 4 gets me 2. So that would be the one that we are typically looking for, right? As a formula. And if it was as simple as just a formula, that would be correct. But here's a little rule that you have to follow. Sample sizes have to be bigger than or equal to 30 before we do any of the things that we've been doing. And if you think about it, it makes sense. Let's be silly. I decide to do a sample of 2 people. Right? I want to get the average age of Americans, and I just decide to ask 2 people. Would it seem reasonable that that sample size is too small to do any sensible estimates? Now, you might think 10 is good. Well, it's better than 2, but 10 people's not good. And we've just discovered through practice, you know, doing it often enough, that you need to have about 30. So mathematically, that's correct, but no, the sample size is too small. Yeah. Suppose you have a sample of 100 and another sample of 225. They're not even telling you what the sigma is equal to, but you don't need to. Which one of these 2 will have the smallest standard error? Remember, that's sigma over root n. Will a sample of 100 have a smaller standard error, or will it be 225?
225.
And you move on, because that's right. Isn't it true that the bigger the sample, the smaller the standard error? Right. Sigma's the same. The only thing that changes is the number underneath. And here is, pick one of these sentences to describe what you've got here. This one I have to do. So I'm just writing down the numbers so I can work with it. So this is a little bit different. It's a little puzzle, which I like. The standard error, I like that. If you want to call it that, go ahead, it's the same guy. But to me, standard error is just easier to understand. Suppose you have a population where sigma is 20, and you want the standard error to be 5. How big should n be? In other words, what kind of sample size do I need to get the kind of accuracy I'm happy with, right? So can you imagine 5, 10, 15, pretty vague, but I'm happy, you know, I'm not going to spend a lot of money. This second one's going to be much denser. Well, the formula is this guy. And this will look a bit like math. This guy is 5, this guy is 20, and this guy is the square root of n. So although you don't get an awful lot of math, you do get now and again some. The math that we're talking about here is solving an equation. I'm going to make it a little bit easier for you by doing that. And that's a clue to what's going to happen next. What do I need to do next to eventually get the value of n?
Would you multiply, like multiply the two sides, like cross multipliers?
You do. What should I do next? Feels like a Math 99 class, right? What do I do next?
Divide by 5 on both sides.
Be careful. The square root of n is 4. What do I do to both sides to get n?
Square it.
Right? Not square root it, which would be 2, but like you said, square it. That makes sense? Square root of 16 is 4. Technically, and that's too small, but I guess the book ignores its own advice. Right, let's do a standard error of 1 then. It should go a lot quicker. If that's going to be 1, oops, that number there is 20. Cross multiply, square root of n equals 20. N equals 400. That's a pretty big jump in sample size, isn't it? If you're happy with plus or minus 5, you only need, theoretically at least, you only need 16 people. And if the standard error that you're looking for is 1, you know how big your sample size has grown to. Now, I want to tell you something else just to make your life even more difficult. Remember the rule that n has to be greater than or equal to 30 to be able to use it, right? To use our stuff. There is an exception. But if the population is normal, right? Normally distributed. You can actually use any value of n you like. Isn't that rather annoying that it's such a awkward rule? Right. Yes, it has to be greater than or equal to 30. But if it's a normal population, you don't need to worry about that rule. Yeah, it's a bit like, I don't know, how many days are in each of the months, right? It's messy, to say the least. So if the question doesn't mention that the population is normal, this 30 equal to greater than 30 will be your rule that you will use. On the other hand, if it does say that the population is normally distributed, you can actually get away with, theoretically anyway, any sample size. Me personally, I would still never do a sample size of 2, no matter what the thing was. Right. But theoretically, it's allowed. Are we good? Right, now, this is a version of question 16. The mean is 6. And there are 2 different samples going on in question A. The population mean happens to be 6. You're given that as a truth. If you do a sample size of 49, what will be the mean of your sample? It will still be 40. It'll still be 6. And won't it also be 6? And if it's 220 people in your sample, won't the mean of your sampling distribution remain fixed? Isn't it always going to be that guy? Now, suppose we then give you this question, which is not as obvious. Suppose you find the probability that you get a mean greater than or equal to 7.5. For which distribution is this number smallest? In other words, would it be a sample size of 49 or a sample size of 81? Which one would give you the smaller fella? Right. So this is me trying to make sense of that. Here is 6. If this fella was 49, can you imagine the sampling distribution might look like that? If you use more people in your sample, what happens to the sampling error? Does it get bigger or smaller?
It gets smaller.
And if it gets smaller, can you imagine this thing being crushed a little bit and then going a little bit taller? So maybe I should put it in the same picture. So that's what an 81 looks like, and the blue one is what a sample size of 49 looks like. Now suppose you take a number like 7.5, which let's say 7.5 is, let's say 7.5 is about here. Can you see that that red guy is almost nothing? Whereas the piece that's under this fella, the blue guy, is a lot bigger. So that fella, which is him, is a smaller answer. So after all that hard work, which one is smaller? Sample size of 81 is smaller. So even although you don't tell me sigma, I can still make an intelligent conclusion about which one of these 2 would be bigger, which one of these 2 would be smaller. I'm checking our time here. Hopefully I've got enough time to cover this. This is our next question. This is 17. Coal is carried in a mine in West Virginia to a power plant in New York, in hopper cars on a long train. The automatic hopper car loads it set to 53 tons. And the standard deviation is 1.2. Okay, that's the population. Question A says, what's the probability that you get one car chosen at random has an X value less than or equal to 52.5? Now, this question has no sample contained in it. So I'm now going to move over and show you what this guy looks like. Now, there is a sample coming later, but not yet. So when you just have one person from a population, and the mean is 53, and the standard deviation is 1.2, and you're looking for what's the chance that you get a value less than 52.5, the answer comes out to be about 0.338. You comfortable about how I did that? It's one person, no sample. Now we're going to change the story. In part B, "45 of those trolleys are taken together." And, okay, my darn thing's gone on me. That way I can't remember the rest. Oh, here we go. What's the probability that you get a mean less than 52.5? Now, it might look the same, but that question is not the same thing. All right. So how do we adapt to this storyline? I've lost you guys. Are you still here? Oh,
Yeah.
God. Oh, I'm bouncing about. I've got about 4 windows open here. I don't know what I'm doing half the time at the best of the time. Right. So let's set this one up. This is a sampling distribution. How do I know? Because I'm talking about a sample, right? Now, I know what the mean of the sample is. Isn't it going to be the same as this guy, 53? I like to call it the standard error, but if you want to call it that guy, you can. What's the standard error? Sigma over square root of n. 1.2 over the square root of 45. That's what calculators are for. 1.2 divided by the square root of 45. Oh, what the heck? Square root 45. And after a lot of hard work, I get 0.179 roughly. So I am going to be looking at what's the probability that this guy is less than 52.5, working with a mean of this number and a standard error, which is just a standard deviation of this number. Do you think the answer I'm about to get is going to be bigger or smaller than this fella? What do you think? The chance that you get one truck is about 33, almost 34% of the time that's going to happen. What's the chances that the average of 45 of them does the same job? Well, I'm going to assume that it's smaller. So the mean is 53, that's good. The new value for the standard deviation, also called the standard error, is 0.179. And what's the chances that that guy is less than 52.5? And the answer comes out at 0.0026. So you can see both answers together. Wow.
Can you
Isn't this
do salt real quick? Sorry.
Yeah, say it again.
Can you go back to salt real quick? I was trying to look at it, but the screen had like froze, so I couldn't see what you were doing.
I can do that.
Thank
I
you.
will. Right. So are you looking at the screen again? Can you all see that? Right. The mean is 53, so I type that in. The standard error, 0.179, I put that in. Less than 52.5, so I picked the left tail. It's a tiny little sliver. And the answer came out as 0.0026. That is about 100 times more unlikely. That sounds like a contradiction in words, but very, very unlikely event. Getting one of them, yeah, anything can happen with one, right? Just doing an analogy. You're wondering about the average age of people in America. And I decide to just pick one person. No, it doesn't happen a lot, but couldn't I pick a 100-year-old person? Could happen. I bet you there's at least a couple of 100-year-olds in Bremen, right? I could get lucky. It's not zero. What's the chances that I take a sample of 100,000 Americans? Right, 100,000 of them. And the average age was 100. It's not going to happen, is it, really? Not in real life. Do you see that it's the same number, but a sample shrinks the variability. And the bigger the sample, the more you shrink it. In fact, if you make a sample big enough, don't you shrink it down to the point where your sample is pretty much bang on top of the population mean? So you know your sample and the population mean are very likely to be the same guy. We good? Right. I'm going to do this moving windows around, which probably means I'm going to be confused for the next few minutes. I'm just trying to find out which window I've got. We are good. I got the right window. Okay, we got about 10 minutes to do about 5 questions, so fingers crossed I cover them all. Question 18. Suppose the height of 18-year-olds is approximately 69 inches and the standard deviation is 4 inches. Do you recognize that's them telling you the population mean and the population standard deviation? Pretty much a lot of the questions start that way, right? What's the probability that a single 18-year-old is between those two numbers? Can you see that that is not a sampling distribution? Isn't that simply just get between, use these two numbers untouched? And then the second one does the same basic story, but 19 people were asked. So would the standard error not be 4 inches anymore, but be 4 whatever the square root of 19 is? And so the answer to A and B will be different. And then C is basically getting us to talk about why that's the case. In question 18, here is your mean and standard deviation. right, for the population. One person, less than 40, right? Pretty much the way these questions start. Sample 3, do the answer. Sample 5, do the answer. Talk about what you see. If you're interested in what's going on here, do you know that when you get things like your blood tested, for instance, or your blood pressure, or your body temperature, they very often don't take one temperature. Do you know they may take your blood pressure, well, with me it happens anyway, where the person takes my blood pressure and then the nurse, not the nurse, the doctor takes my blood pressure a second time, and you might think, why do they do that? Well, isn't the average of 2 blood pressures more likely to be the realistic number for my blood pressure than just taking one person?